If you are watching this video, you've already developed skills in writing SQL queries for one table at a time. Now, that's good, because what we'll show in this video tutorial builds on those skills. Yes, working with the group by clause can get confusing, such as forming groups and listing just the right columns and aggregates in the select list. But working with multiple tables in the same query, well, that's like jumping to the pros after your freshman year. The game just got more challenging. Hi, I'm Jeff Hoffer, one of the co-authors of Modern Database Management. This video tutorial, second in a two-part series on SQL, is meant to assist you to develop ways to formulate SQL queries that involve linking multiple tables and extracting data from several tables to form the answer table to a question. We'll show in this video several ways to link or join tables, and the important and powerful capability of SQL called subqueries, both correlated and uncorrelated. I hope from the visualization techniques we'll show, you will develop a clearer feel for conceiving of the possible structure for queries that require multiple tables. You should find value in this video tutorial before reading about multiple table SQL queries in the textbook, or during your first reading about this topic. The examples in this video are more complex than those shown in the first SQL video. Thus, you should have had some practice writing simple SQL queries before viewing this video. Let's jump right into one type of multiple table query that also involves combining the results from several simpler queries. Consider the following question. The production manager is concerned about whether there are enough employees who have all the skills they need to do critical jobs. One such query he has in this area is to display the name of employees who have 12-inch bandsaw skill but not router skill. Thinking about this question, part of what we want seems to be rather straightforward set arithmetic. We need to find the set of employees with 12-inch bandsaw skill and then eliminate from that set any of those employees who have router skills, another set. What is left are those with the bandsaw skill but not router skill. That is simply one set minus another set. Fortunately, SQL has operators for set union, intersection, and subtraction. So we can start by building a skeleton with pseudocode for our query. We'll say we're going to write a query to show the names of employees with 12-inch bandsaw skill. And then we're going to subtract, using the minus operator in SQL, from that a set which is produced from a query to show the names of employees who have router skill. Minus is the set subtraction operator that we need to use in this case. Each of the two queries will be quite similar, so once we figure out one of them, the other will almost write itself. We need to show the employee name, which comes from the employee table. So we'll open that up here in the directory tree. And we see employee name there in the employee table. But what skills an employee possesses comes from the employee skill table. So let's open that up too. And we'll see the columns in there. So that's where we see the skills recorded. The employee skills table has skill ID, but we need the description of skill, so we need to find that in the skill table. So now we have on the screen all the columns we're going to need. Thus, we need to join employee with employee skills, and then to skills to match an employee with a description of a skill he or she possesses. What we want to to produce is a set of employee names. So the select clause is easy. We'll put that on in this first query. So we want the names of employees. So we'll say select employee name. And based on what we just said, we need 3 tables in our query. So the from clause is going to be from an employee table, and I'll give that an alias, an employee skills table, and the skill table. Giving aliases to all those. You'll see in a moment how the use of these aliases are going to simplify the rest of the query we have to write. You'll recall that with relational databases, tables are related by foreign key to primary key cross-references. We can see from the directory tree that employee and employee skills are linked by employee ID. The columns names don't have to be the same in the 2 tables, but they are for our database. The foreign key and primary key columns just have to come from the same domain or set of values with the same meaning. And employee skills and skill are linked by the common column of skill ID. So each pair of tables in the chain from employee to employee skills to skill is linked or joined by a common column. That is, 3 tables will have 2 links to form the chain, with each link or join defined by the common foreign key to primary key cross-reference. SQL has several forms of specifying joins. We'll use in this example the form in which the joins are specified in a where clause. With 3 tables to join together via 2 links, we'll need 2 parts to our where clause, one to specify each join. So we add the following to our first query. Where the employee ID from the employee table is equal to the employee ID from the employee skills table, and the skill ID in the employee skills table equals the skill ID in the skill table. Because the column names are the same in each pair of join statements, I have to clarify for SQL which tables the columns come from, and I do this by prefacing the column name with the name of the table where SQL should find the column. See how the use of aliases reduced what I had to type? Now, this first query is to find employees who have the 12-inch bandsaw skill. So we are not interested in all the skill table rows, only the one for 12-inch bandsaw. Thus, we need to add another qualification to the where clause, which would be and we look in the skill table and look at the skill description and make sure that that is equal to 12-inch bandsaw. So now we have a query to produce the first set of employee names we need, those employees with 12-inch bandsaw skill. With this query structure in place, let's fill in the second query, which wants the names of employees, this time with router skill. The query will be just like the one we just wrote, changing the skill description qualification value. So this will be, and what I'm going to do is copy this first part, move it into the second part, and change the qualification to router. Now, to make sure that there's no confusion with for SQL, I'm going to change all these aliases so that this second query clearly refers to different tables, and this way, or the same tables actually in different roles. And this way I'll make sure that SQL doesn't get confused. Now when I execute this query, and now I don't need these parentheses either. When I execute this query, I will find that there is one person that satisfies the qualification. You may have conceived of this query in a different way. Well, that's okay. I've seen from my students several different SQL queries to produce this same result. Other than possible computer, primarily disk processing efficiency differences, any correct query formulation will do. If the query were to be run frequently against a large database, then efficiency might matter, and it would be good to test several formulations to see which would perform the best. Our next example involves multiple tables, but in a different way. This question is, which customers, and show customer name and customer state, are from a state that does not have any salesperson who lives in that state? Okay, how can we approach this question? Probably the most straightforward way is to again think of sets, and we can write the skeleton of a query in pseudocode to do so. This would be query to show customer name and customer state for customers not in any state where a salesperson lives. You are probably familiar with the use of the SQL operation not in from single table queries. What this skeleton of the command says, making use of not in, would be query to show customer and customer state whose customer state is not in, and then we'll have another query, which is a query to list the salesperson states. We are comparing customer state with a set of values for salesperson states. These are not the same columns, but their values come from the same domain. Hence, we can make this comparison. In this query, we have the result of one query, the list of salesperson states, being used to qualify what goes into the result of another query. The query with our final result is called the outer query, and the other one, yes, you guessed it, is called the inner query. Let's fill in the inner query. That's going to be fairly straightforward. It's going to be select salesperson state from salesperson. What we want to compare the result of the inner query to is customer state, which we do via a where clause in the outer query. So we'll make some changes there. Where customer state not in, and then not in the set of values from the subquery. Now we just need to clean up the select clause of the outer query, so we get as our complete query select customer name, and we don't want the word and, just the comma, customer state, and we have to say where we want that from. So that comes from customer, where that customer state's not in the result of that inner query. The data used in the outer query comes from only the customer table, so we don't need to mention the salesperson table there. To the outer query, the inner query is simply a set of values, like any list of literals we might have within the parentheses. Now, when we run this query, we get a very fortunate result. No rows. Thus, every customer is in a state with a salesperson. Now, let's mix things up a bit with yet even a more complicated multiple table question. The question is, list all the product lines by name and the number of products in each line. Include all product lines. Well, what do you think is the significance of the last phrase, include all product lines? Why would some product lines be excluded from the result? Let's remember this facet of the question, but we'll come back to it later. We'll build up a skeleton of our query with pseudocode. The question asks for product line names and the number of products in each. So our select will be something like the following. Select product line name, and then the number of products in this product line. Where do we find this data? Well, product line name is going to come from the product line table. So let's open that up, make sure it's there. But the product line table does not itself include any data about products. But the product table, and we'll open that up too, contains the product line ID, which allows us to link a product line with all its products. So we'll need these two tables, and we'll need to join them on their foreign key to primary key common columns. In this case, product line ID. Now, more of our query is taking form. We can add to our query a from clause. From product line and product. And I'm going to give these aliases again in case it saves me some typing later. Before, we used a where clause to join tables. In this example, we'll use the other most common joining method or syntax, which is to indicate the joining within the from clause by telling SQL what columns to join on. There is another syntax available with some SQL systems called using. So you should investigate that form if it is available to you with the DBMS that you're using. The on part of the from clause looks a lot like what we say in a where clause. So we can modify our query as follows. We're going to say from product line, and we'll say some kind of join, which we don't know yet what it'll be, with the product table. And then there is an on clause, which says what the common columns are. So in the product line table, we're going to use the product line ID, which is the primary key of that table, and we'll match it up with the product line ID, which is a foreign key in the product table. As described in the chapter on Advanced SQL, there are several types of joins, the most common of which is inner. Maybe that is what we need. So we'll use that as follows. So the some kind of join becomes an inner join. we will need to figure out how to compute the number of products for the product line. You may recall in the first video we used a SQL built-in function called count to find the number of things. So let's try that again. When we use an aggregate function like count in the select list, it is almost always to be a count for some group. Yes, that's what we want. We want a different count for each group identified by different product line names. So we need a group by clause too. We want to count the number of products, which we can do by counting the number of product IDs associated with each product line, which we can do because of the join. Thus, our query becomes, our count here is a count of product IDs and it's from the product line table interjoined with the product table on that join condition, and we have to group by the product line name. Well, let's run this query and see what we get. Well, we get a result. And that looks pretty good, but we still haven't explicitly dealt with the pesky last phrase of the question. Include all product lines. Have we included all product lines? Well, we show 5 product lines in this query result. Let's run a simple query to show all the product line names to see if any are missing. And that simple query will be select product line ID, product line name from the product line table. And oops, we have 7 product lines. Where did the other 2 go? Well, let's see what products are in these 2 missing lines. It happens to be products lines 6 and 7. I remember which ones we had before. So we can find this via another query. We'll look for the product ID from the product table where the product line ID is in the list of 6 and 7. And we'll run that query. An empty answer table. Well, what does that mean? Oh, of course, it means these 2 product lines have no products in them. They are defunct or future product lines with no products. So when the query we wrote for the question, and I will go ahead and restore that, when we executed that, it didn't find any products for these 2 product lines and hence left them off the query result. How can we get them there? Because we want to know the number of products for every product line, even those with no products. The answer is another SQL feature called outer join, which is not an inner join. An outer join says include in the result a row from one table, even when it has no match with any row from another table. The direction of this statement matters. We want to include a product line row even when there is no matching product row matching on product line ID. So we want to include rows from the first or left table in our query where there is no match with the second table or the one on the right. Thus, our correct query will be, instead of inner join, it's going to be a left outer join. And now, when we execute the query, we see all 7 rows, including the 2 that have no products in those product lines. The final query we'll use to illustrate multiple table queries is the following. List the name of every customer and the date of their most recent order. Pretty simple request, huh? Well, it's not so simple of a SQL query. That's not uncommon. Sometimes the grammar of SQL and that of natural language aren't so parallel. Let's start by creating a skeleton of pseudocode for the query and see where that leads us. The first skeleton will probably be quite simple. I think it could be, we want to select the customer name, and we want to show the date of their most recent order. Where do they find these data? Well, we know that customer names in the customer table and order dates are in the order table. I'm not going to open those up this time. So we can expand our skeleton query to include the 2 tables, and we might as well indicate how to join these tables, since from our previous examples we're pretty comfortable doing that now. So we're going to say select customer name and this date from the customer table and the order table. Again, I'm giving them aliases to simplify some subsequent typing. Where the customer ID in the customer table is equal to the customer ID in the order table. That's a good start. Obviously, the rest of the query is what is interesting. The date we want to show for each customer will be different because it is the most recent order date for that customer. And it has to be the most recent, or we might say maximum, of all the order dates for that customer. Ah, there's the rub. We don't want the customer who has placed the most recent order, but rather we want the most recent order date for each customer. In other words, we have to find for each customer the maximum order date for that customer and use that date among all the order dates for that customer in the query result. Okay, so we want to display an order date. Hence, we can change our query as follows. And I'll give that an alias 2, indicating that it's really going to be the most recent order date. So that's going to appear as the column name in our answer. But which order date? Again, we haven't computed that. Well, the one which is equal to the maximum order date for that customer. Well, it seems like a where clause component to me. So still using pseudocode, we could have, and we want the order date that's equal to the maximum order date for this customer. This customer meaning the one in the row we're displaying in the answer table. That is, we need to compute the maximum order date for each row of the select statement, which will be our outer query. But the inner query is a little different each time we compute it, because it has to apply to a different customer, the one for the current row we are trying to display. Which row is that? It's the one for c.customerName, the column we are displaying. Thus, in the inner query, we want to tell SQL to scan through all the orders for the current c.customerID, customer, and find the maximum of those order date values. That's the one we want to display with this customer name. That actually is not a difficult query to write once we realize that we have to refer to the current row of the outer query. Thus, the query can be modified as follows by defining this inner query. We want to select the maximum of the order dates from the order table, and I'll give it another alias now because we're using the order table in a different way. Where in this order table, if I look at the customer ID, it's going to be the same as the customer ID from the C customer table. In other words, the current row in that customer table that we're showing. This is called a correlated subquery because to compute it, we have to correlate what's going on in there with a row in the outer query. So now we are getting close to what we need. So to summarize, we're using the order table in two ways, in two places in this query. Once in the outer query to join the customer and order tables, and then again in the inner query. Thus, we are using two different aliases to make sure SQL knows which role the table plays where in the query. It's like there were two order tables. The where clause of the inner query limits the scan each time the inner query is run to the current customer name from the outer query. This scan finds the maximum order date among all the orders for the OX order table that have C.customerID as their value for OX.customerID. Now we'll execute the query. And we'll see the results. Well, why do some customer names appear more than once? Because there are multiple orders on the same most recent day for that customer. How can we get rid of the duplicates? Remember the SQL keyword distinct? Let's add that to the query and see what happens. And we'll run the query again. And now we get only one row per customer in the answer table. That concludes this tutorial on multiple table SQL query construction. We've seen that thinking in terms of manipulating sets is at the heart of developing a sound query. Also, writing the query out in skeleton form with pseudocode and building up the components of the skeleton one by one is a good way to break the problem into manageable pieces. We've also seen that looking at the data and visualizing the data needed in the query can help us to figure out how to join, group, and compute the data we need. We've seen how joining data in several different ways using the where and from clauses allows us to not only join tables, but to do so with both inner and outer joins. Finally, we showed how to use inner queries to produce results needed by an outer query, and that sometimes the computation of the inner query is dependent upon the data to be displayed from each row of the outer query. When learning SQL, there is no substitute for writing lots of queries. Even if not assigned by your instructor, try to write each problem and exercise query at the end of the SQL chapters. I'm sure your instructor will help you when you get stuck.